Hello, I would like to give a short presentation about the challenges of analyzing performance metrics in supply chains. And I'm going to contrast the dashboard approach with the approach that is used very typically in the quality control or quality assurance area, which is more of a process-oriented approach. I'm going to start by going to a spreadsheet that I developed that just is meant to illustrate the challenges. And so I'm sitting here as putting myself in the place of a new supply chain analyst who is looking at quality data from a previous month. And I'm new, so I've noticed that for example, for service level in the last month, the goal was 78% or better, and we had an 80% rate, so we got a green, which would indicate that we met the goal. So I'd probably take that as a piece of information that was interesting and then wait to see what happens next month. And so let's say in January I come along and the rate is 82%. It's green because it's met the goal of 78%. So I'm feeling like there's nothing I really need to do to concern myself with this metric at this point. Then February comes along and it's back to 80%, so it's pretty close. And then March comes along and it drops to 72%. So we've just had 3 months in a row of 80%, even though I may or may not remember that because I'm looking at a lot of data. But what I do see here is that I have a red, and I have a red that's 6 percentage points below the goal. And so my assumption is that someone in this position would take some action. And the action that the person might take might be to make a few phone calls to find out what's going on, perhaps put a team together to see if they can find the root cause of this problem and correct it. And so let's assume that one of those things happens, and April comes along and the rate jumps all the way up from 72 to 86%. I'm assuming that the analyst is very happy at this point and the team's been successful. Perhaps there's some bonuses to be given out, or at least some pats on the back. And then May comes along and it's still 86%, so everything's great. June comes along, 88%. August comes along and it drops to 64%. Oh my gosh, it just dropped from in the 80s to in the 60s. So obviously something's wrong. We have to do something about it. We pull the team together again. September comes along and it goes up to 80, and then we're green again. Okay, so notice, well, without belaboring this, that there's been changes in color here indicating action that we would take, and I think the way I've described it is a very reasonable set of actions. And we've noticed that the 2 times that we put this team together, this we've been successful in bringing back the service level where it needs to be. Now I'm going to let you in on a little secret at this point. These data were not planned ahead of time. They were actually randomly generated by the computer, by Excel. I'm going to show you the nature of the random generation of the data. So if I click in this cell here, and it says data generation, which is another tab, B14. So let's go to data generation tab, and here's B14, which is the percentage of on-time deliveries. And that is coming from the numbers on time, which is the 40, and the number of deliveries, which is 80. Well, where are these numbers coming from? Well, if you go up here to this set of 50 numbers, each one of them looks like the first one. It says RAND, parenthesis, parenthesis, which is Excel's way of generating a random number between 0 and 1 on a continuous scale. So it would be a minimum of 0, a maximum of 1, and it will be uniformly distributed. So there'd be no tendency towards the middle of that range or the ends or anything else. It'd be just a flat uniform distribution. And then what I have down here under number on time is, it says count if A1 through E10 less than 0.8. In other words, what I'm doing is I'm counting how many times that random number of those 50 is less than 0.8. Well, it turns out that if you, little manipulation in your mind here, that 80% of the time I'll get a number less than 0.8, which means that this random number generator will give me a value of 80% on average, but it will be random. So for example, if I just let it generate another random number, you notice I got a 78. And if I generate another set of random numbers, I got a 76. If I generate another set of random numbers, I get an 86. You see those numbers are vary. And the big secret that I'm letting you in on is all the color changes you saw up here were driven by the normal variation in 50 data points that have a probability of success of 80%. So nothing changed in the process. In other words, if we translate to the real life scenario, it would be as if nothing changed in our way of doing business, yet the performance metrics were changing, which seems to make sense because they should be some randomness, but because of the color changes, which really meant nothing because it was the same process with the same probability of success, we took a lot of action and we attributed the action to changes coming later. And so at the very minimum, we don't have a good fundamental understanding of this process. We have some very irrational suspicions about what we've done to make the process better. And in fact, if we would have just left the process alone, we would have got the same exact values. So let me go back to the PowerPoint because I just want to continue this farther. And what I want to do is I want to take a little bit of a step back and just talk about a new scenario which is very similarly focused, where we have service level data for 20 months and the goal is 78%. And if we put a red, green, yellow scheme on this, where 78% or above would be green, red would be 76, or I'm sorry, less than 76%, and if we got a 76, we'll put a yellow because we're close to the 78. So you see here that we have a mix of green, yellow, and reds. And again, a reasonable person might say, well, this process is really changing. Some months it's doing well, some months it's doing poorly, and we have kind of a process that really is not stable. It's a chaotic process. Well, let's dig deeper into this. First of all, if we do a run chart of these data, in other words, if we take simply the 76%, the 86, the 68%, this is also called a time series plot, you get a pattern like this, right? Here's the 76%, here's the 80, here's the 68%. So if you look at this set of data, it bouncing around, average is 79.6%. There are 50 orders shipped per month in this data set. And these are the number that were percentage that were on time. And if you looked at this, many of you might say, well, wait a minute, that just seems to be randomness bouncing back and forth. But how do I know the randomness that's bouncing back and forth is not excessive? Like, in other words, how do I know there's not something fundamentally different about what's going on in my business in the month 3 here where I had the 68% versus the month 13 where I had, above 90%? Seems like they're totally different. Well, let's again dig deeper. If I go into probability theory, there's something called a binomial model, which represents the variation you would expect in the following scenario. You're running discrete trials, in other words, in my case, discrete orders, and each one has a certain probability of success. That's exactly what we're dealing with in this situation. It's analogous to, flipping a coin that has an 80% chance of getting heads. It's a similar kind of a situation, but we're dealing with on-time deliveries. And notice the average here was 79.6. Well, if I use the theory and I put in the 79.6 value into the binomial model, this shows the spread of the outcomes I should be expecting on a month-by-month basis. In other words, according to this, I shouldn't be surprised if I got like a 70% or a 92% because it's all within the range of variation. So now, and by the way, the average for this histogram here is 79.6 because that's the probability of a success, and the standard deviation is 5.6, which is calculated from this histogram. It's all theoretically based. Also, you probably noticed that it looks like we're dealing with a bell curve here. So what does this all mean? Okay, well, it does mean that if I could superimpose a bell curve on here, it seems to make a lot of sense. So the normal model applies. And if I go back to that run chart you showed earlier, and I kind of take that histogram or that bell curve and I kind of superimpose it on the left axis, in other words, what I do is I take the horizontal axis here and make it the vertical axis here, you notice that my question that I need to ask myself is the pattern of the run chart consistent with this bell curve? Because the bell curve would say that the process here is not undergoing any fundamental changes, that these data changes you see are just random. So how do I make this into a practical scenario? Okay, very easy. First of all, if I again flip this thing around so that the service levels are on the horizontal axis, and here's my bell curve. Remember, the average is 79.6 and a standard deviation is 5.7. I can come up with what's called zones. In other words, here's the average. And if I go one standard deviation above and below the average, I expect 68 of the values to be within that range, according to the bell curve. If I go two standard deviations, in other words, 79.6 plus 2 times 5.7, so I end up with around 90% and around 68%, I know that theoretically 95% of the values will fall within two standard deviations. And in turn, I know 99.7% of the values will fall within three standard deviations. I could use this information to superimpose these zones on a run chart and then apply a set of rules based on the normal distribution that will statistically determine whether or not the process has undergone any fundamental changes or whether the data we see are just varying randomly. And here's what that result would look like. And this is called not a run chart, but a control chart. It's called a control chart because we have a center line representing the average of 79.6, and then we have the control limits here, which are about 96% and about 63%. And I show the intermediate zones, the one standard deviation, two standard deviation zone, by the dashed lines. And there's a set of rules. I don't need to go into the rules, but the point is that the rules would not be violated here, meaning that I would confirm that this is a stable process. And what that means is that the process is not changing, which is similar to what you saw in the simulation in Excel. So the flow chart of this type of process orientation would look like this. I would collect data, and instead of asking if the goal's been met, what I would say is, has the process changed? And you would know the process would change from the control chart that would give you values that were, outside of these zone rules that would be put in place for the control chart. And if I did find that the process changed, I would ask why, and I would hopefully find the root cause of the problem very quickly. The problem we had in the simulation at the beginning of this presentation was that we went from green to red, and the process had actually not changed. It was the same process, so nothing changed in the system. So it was not a good idea to do that because there was nothing fundamentally different. Now, if the process does not change, you may be asking, well, wait a minute, just because your process is stable doesn't mean it's good. And you're correct that that's true. So the secondary question here is the process acceptable? We could only really answer that question if the process is unchanged, meaning that it's stable. And if it is not acceptable, we can try to improve it. That's where we put the team together. And then if it is acceptable, we set up a monitoring plan and we just kind of keep going around in a circle here. So to conclude this exercise, this presentation, so in the data set that I just provided, the probability that a delivery is on time is 79.6%. And this rate has not changed in the past 20 months. Since the goal was 78% or better, the process meets the goal, and so we should be happy with this process at this point in time. So essentially all that action we took was worthless, it was not needed because there had been no fundamental changes in the process. And an old colleague of mine, old professor of mine, Frank Kaminsky, used to say the thing people need to understand about looking at data to make decisions is very often the data changed, but the process remained the same. In other words, we have to understand that performance metrics vary randomly, and therefore we have to understand whether or not the random variation we see, we have to understand whether that's due to process changes or is it due simply to the normal variation we would expect in that process. And now in this course, we're not going to get deeper into that, but this is something that I think you really should be aware of, because I hate to talk about the development of performance metrics and their implementation without talking about the potential pitfalls of an analysis approach that is not valid. Okay, well, thank you very much.